Okay, so what about this? Have a look, please. All right, so what's the range of this function? Now, how do we, before we even jump in and give me an answer, how do we think about range on a graph? Okay, how high or low it goes. Range is the set of the output values, the y values, right? So we're looking at this vertically now. We want to know what are all the values of y that are represented, so that the vertical coordinates, second coordinates of all of the infinite points on this graph that are represented on the blue graph. So remember, we had kind of a little model. We could think about it. If we took this thing and we smushed it onto the y-axis, what would the stain on the y-axis look like when I do that? And what's probably the big question? Everybody gets most of it, but there may be a little bit of uncertainty about what? Does it ever get to 3? Exactly. So it's pretty clear that it's going to go down forever from 3, but are we going to put an open or a closed endpoint?
Open.
It's open. Yeah, it's open. And how come? Now, let's think of the behavior of an asymptote. An asymptote is a boundary line that the function is going to approach but never cross. Now, can it cross? Yeah, it can. There's no reason that it can't. We could do a function like, for example, if I were to do maybe something like this, like if I did like sine x over x, what that would look like on the xy plane, it would just kind of look like, so what's the asymptote there? That's a weird one. It does cross it an infinite number of times, but what is the function? The meaning of an asymptote is it describes the end behavior of the function. So if I were to go out infinitely far to the right or to the left, what y value would an ant walking on this function always be approaching? 0, right? So if I were to graph the asymptote would just look like the x-axis this time. Yeah, it's crossing through it an infinite number of times, but as we get further away, each oscillation of that sine curve, and you guys haven't really talked a lot about sine, that's kind of the next year thing. But each oscillation is just going to get damped more and more and more and squeeze closer, closer and closer towards that asymptote, right? That's an unusual one. That's a sine function is an oscillating function. We don't really deal with a lot of those this year. This year we're dealing with things more like this. This is one where we're just approaching that asymptote from the bottom, and it looks, and I can just hear people thinking this out loud. It looks like it touches the asymptote, but is the graph meant to be a perfect representation? No, it's really just a graphical organizer for us, right? We can't draw it perfectly. We're limited by the resolution of the computer. We're limited by the window on which we can view this thing. But you get the idea. It's just going to nudge up against this thing more and more closely, and it goes back to that example that we talked about last week. If for every second for the remainder of time, if I were just to cut my distance to the door in half every second, do I ever get to the door? No, I never do. But I'm always approaching it. You could say that the door is the limit of my motion. The only point that I will never get to is the door itself. Every point in between me and the door, there's not a point that you could indicate with an infinitely fine Sharpie that I wouldn't eventually step on. Right? There's no point I could make on the floor that I wouldn't step on as long as it's not actually at the door, right? So the door is the one place that I never get to, right? It's a weird concept. So then how would I write this range as an inequality? Say it again. Okay, y, it's got to be y, doesn't it? Because it's a range. So it's got to be y is less than 3. Good. Okay? Good. How about something like that? What's the range of that function? Now, there. greater than 6 and less than 10. Okay, so we're writing this as an inequality. Now let's throw that up there and we'll discuss and see if we like this answer. So it's a range, so I'm going to have a y, right, is greater than 6 and less than 10. What do we agree with and disagree with on that? What do you think? Yes, ma'am. Okay, good. So the endpoints are good, but the ant actually could stand at this point right here that has a y-coordinate of 6, and he could stand at that point that has a y-coordinate of 10, right? So we must actually include those points there, right?
What about the thing you said that
Say it again. With the asymptote thing?
Yeah.
Okay, but is there an asymptote here?
I don't know what that.
So the asymptote is that line, right? So an asymptote, even though it's not physically a part, I mean, none of this is physical, but even though it's not a, technically, it's got taken down, even though it's not technically a part of the function, you gotta keep the key count going on your own, I guess. The asymptote is a really important part of the function. The function never actually touches it, but if there is an asymptote on a function, we really need to draw it in there, right? And when we get up to calculus, all you guys get up to calculus, one of the things that we'll do, when we want to explore end behavior, we'll kind of think about functions on in different places. So we'll think about, if I'm given some function f of x, and I want to do analysis of this function, so I want to sketch a curve. And we talk a lot about curve sketching in calculus because we don't really care what it looks like exactly. We just want to know the locations of the important points. The maxima, the minima, and the points of inflection and those kinds of things. Sometimes we'll look for zeros. Sometimes we'll want to know where y-intercepts are depending on what the function means. What are we going to do with it? But we can sort of divide it up into regions. We can talk about the local behavior. Usually that's pretty action-packed. So the local behavior, the behavior around the origin, when I say around the origin, that's all relative, right? If we're talking about a function where the inputs are large, maybe we're talking about population size of rodents or something, and then there might be hundreds of thousands of rodents. But still, hundreds of thousands, those numbers might sound big compared to like the numbers we use to count things, but they're small compared to the numbers of stars in the galaxy or something, right? So when we say local, we just mean numbers that are clearly not infinite, okay? So the local behavior can be action-packed, and what I mean by that is it can have lots of stuff going on. We could have lots of things like, we could have lots of peaks and valleys, we can have lots of things happening in there, right? Mathematically speaking, that's pretty action-packed stuff right there. Okay, but, so that's the place we want to explore. But then there's another part of this too. A lot of times we want to explore what we call the end behavior. And the end behavior occurs at the extremes. So the end behavior would be in these bubbles that don't ever end. They just go out forever, right? And in calculus, the way we'll get at that is we'll take what we call limits at infinity. We'll explore the behavior of the function when we let the input variable go infinitely large in a positive or negative direction. And we've got some techniques in calculus for dealing with that. Some of them we'll actually get to this year in Algebra 2, and just take it a little further in calculus. So the end behavior, a lot of times that's going to give us things like horizontal asymptotes, or, we won't do it this year, but even things like scant asymptotes, where we get asymptotes that are on an angle. Okay. So these are, a lot of times you can think about these as being sort of the skeleton of a function. And if you can come up with the asymptotes first, then filling in the blanks with all the curlicues and dipsy doodles and peaks and valleys, it gets a lot easier to do, right? So what I mean by that is if I knew, for example, and this, I'm jumping way ahead here. So this is something that, don't think that this is intended to make sense right now. This is just, I'm just giving you kind of a little foreshadowing here about where we're going with this. If I had a function, and let's just say I knew that it had a horizontal asymptote at x equals 3, So if we go up here to, or y equals 3, sorry. If I had a horizontal asymptote at y equals 3, and let's say it had a vertical asymptote at x equals 5. That tells us a lot about the behavior of the function. Just knowing that, let's think about the kinds of things that this function really could do. Now, if it's a function, it can't violate the vertical line test, right? So, to the right of this asymptote, this vertical asymptote, what really could the function do? There might be some fine behaviors that we're going to miss, right? But on a broad scale, there's really only two things that could happen over here. What's one of them? Exactly, one of them would be it goes like this, right? The function goes like that, right? So it's going to stick to this asymptote, and we haven't talked about vertical asymptotes here. This is totally new stuff. You know, we haven't talked about the math of that at all. But they act the same as horizontal asymptotes. The function's just going to get infinitely close to that as the ant walks closer and closer and closer to the number 5. The one difference is, with a vertical asymptote, do you think you can cross a vertical asymptote? We said you could with a horizontal one, right? It could cross and just get smaller. You think you can with a vertical one? How come? What would the problem be? Vertical line test would be violated. It wouldn't be a function, right? So there's one possibility. The other possibility would just be that it's down there, right? It's either A or B. Take your pick. We could figure out which one it is by using some tools of analysis that we'll discuss throughout the year. Over here, same thing, right? It's going to, on a large scale, it's either got to do that or it's got to do that, right? So getting those asymptotes established, finding them, is a pretty big deal. Okay? We're just taking the first small steps towards that process, that in a couple of years will take a lot further. When we do problems like, like this stuff we're doing, where did we do wrong? Like right there, right? First small step. We're just starting with, we don't know what this graph represents. It's just it just represents some function, right? Some function that we're not told. Eventually, we're not going to be given the graph. We're going to be given the function, and we've got to come up with the same information just from the function itself, not from its graph. This is easier, but it gives us a conceptual idea where we're going with it, right? So we did that. How about this question? Oh, less than or equal to, yeah, that's where we left off, right? So less than or equal to y is greater than or equal to 6 and less than or equal to 10. And the reason is because as the ant walks along this function, the ant can, when the ant stands on that point right there, it has a y value of 6, but that's the lowest it can go, right? That's the bottom of the valley, or the relative minimum. When the ant stands on that point, it's got a y value of 10, but that's the highest point it can stand on. To the left of that, it's lower than 10. To the right of that, it's lower than 10. But 10 is included, and so we have to have those equal signs there. If I were to write this as, rather than an inequality, if I were to write this with interval notation, how would I write that? Yeah, I'd have to have brackets on both sides. A Moodle question. Do you know how to do something like, what if we wanted to know the domain of this? We wanted to write the domain using interval notation. How would you do that in Moodle? Because what's the problem? You got a bracket, one closed endpoint and one open endpoint, right? So in Moodle, all you do is you open up a set of brackets. I'm going to put, what's it going to be, 3, 7? And then even though there's already a bracket there, after the 7, if you just type a right parenthesis, I guess that's how you say it, then that's what you end up getting. Okay? Does that make sense? Okay? What about that? Okay, this is a little different. This is the end behavior part, right? So we want to get at this idea of what's the end behavior of the blue function. This is kind of an algebra 2 notation. As x, that means approaches. The arrow means approaches in math. As x approaches, and I'll write that down up there. This is how we would say this. As x approaches negative infinity, f of x approaches what? Okay. Now, the way we write this in calculus, and I want you guys to see this because you're, I'm assuming, hopefully all going to end up in calculus. So the way we would write this, instead of writing it using algebra 2 notation, we would call this a limit. We would say that the limit of f of x as x approaches negative infinity equals what? Okay. You're right. Okay, how'd you get that?
It's going up.
Goes up forever, right? Simple trend. As the ant goes to the left forever, he goes up forever, right? The left forever part is the first statement, right? That's the x statement. The f of x, just a fancy name for y, isn't it? Right? So the value that f of x approaches is the y statement, okay? Does that make sense? So you're independently describing both behaviors in the extremes. And we go to the left forever, what does the function do? Goes up forever. So the answer is positive infinity. In the language of, and that's how it's going to look on your assignments. But in a couple of years, we would do the very same thing with this problem, and we would use this notation. We would say the limit of the function, f of x, as x approaches negative infinity is positive infinity. Okay? Same idea. Same idea. Okay? I'm not going to write it down up here, but just verbally, as x approaches positive infinity, f of x approaches negative infinity. Because as we go right forever, we go down forever. Right? Okay, same question. That guy. As x approaches infinity, and when we say infinity, that implies positive infinity, right? We don't have to write positive. As x approaches infinity, f of x approaches 4, right? How come? Because that's the asymptote that it's sticking to. Okay, you get the idea? Okay, yes, sir.
So that line is always going down forever,
Yeah.
but even if the asymptote wasn't there, it's still going down forever, but this one does go past 4.
Exactly. So that we could have a line instead. The function could be something that just goes down and keeps getting less and less steep, but never approaches an asymptote. I'll give you an example. Give you an example of one. What if we did something? We pull up Desmos. I want you to see the difference. It's a really good question. Okay, so what if I did something like 4 minus log x? Okay, that looks pretty similar, doesn't it? But guess what the range of that function is?
The range,
Yeah,
positive.
all reals. Y would go from negative infinity to positive infinity on that one.
What does it look like in this one when there is an
Okay, well, in that it's oftentimes it won't really just show you the asymptote naturally. That's one of the weaknesses. It's, I mean, imagine what that would look like. I guess you could code it so it would, and maybe, I don't know, maybe there's a setting where you can turn on asymptotes in there. There might actually be. I'll have to look and see. But when you write a function that does have an asymptote, you really need to draw the asymptote because that's a big difference, isn't it? These look almost the same, but because this one doesn't contain an asymptote, the implication is it's got to go down forever, right? The ant's going to, if the ant walks to the right far enough, he's going to go to negative infinity vertically. Okay, everybody get that? That's kind of a subtle concept, but it's important. Okay? So this one, because it's got that asymptote, it's telling us, there's a roadblock there. That's the point it's approaching vertically. Okay? What about that one? As x approaches negative infinity, f of x approaches. Yeah, that doesn't make sense, right? Can the ant has no place to walk. to get to negative infinity. The ant steps to this, once the ant gets to -7, he just, I don't know, blinks into some other universe or something. There's no place for him to go in this universe, right? So this one makes no sense. The answer would be NA. And I think it's a good question because it's forcing you to kind of reconcile those ideas that end behavior depends on the function going infinitely far to the left or the right. Otherwise, there is no infinite end behavior. Okay? Okay, so before we move on, I want to just put one more, we'll come back to this. We'll probably look at this exact same thing again in a couple months. But I want to show it to you right now real quick too. So, talking about this end behavior, okay, let's just take a quick look at power functions, right? And we're going to come back to this again and again, but it helps to see things multiple times. So if I graph the function y equals x, that's pretty boring, straightforward, right? Just a line, slope of 1 through the origin. If I graph the function y equals x squared, we get a parabola, right? Everybody knew that, right? Vertex is at the origin, okay? It goes through the points negative 1, 1, positive 1, 1. If I graph y equals x cubed, I get a cubic graph, right? There's the green graph, okay? But now you're going to start to see this gets pretty boring. If I go to x to the 4th, well, look at x to the 4th. That's the purple graph compared to the green graph. They look, let me get rid of all the others here for a second. They look pretty similar, don't they?
Yeah.
Right? What if I go to x to the 6th? Those all look pretty similar. Can you describe what the differences are? Just qualitatively, what's going on? Christian, what do you think? I mean, tell me something, Seth.
They're getting steeper and then they're getting flatter.
Okay, so they're getting more squared off, right? What do you notice? Do you notice any symmetry? They all share the same symmetry, which is what? Okay, I heard different ways of saying it. We get line symmetry or folding symmetry about the y-axis, right? But the larger the power of x, just the more squared off the graph gets. The steeper the sides and the more squared off the bottom, right? Okay? What if I were to do the same thing, like you could make a prediction here. If we went from y cubed to y to the 5th, what do you think is going to happen?
It's a little steeper.
It's the same thing, right? It's just going to be more squared off. But in both cases, now, what about this symmetry? We'll come back to this again later, but we're just going to very briefly touch on this. Different symmetry. What's the symmetry here? There is no folding symmetry, is there? There's no place I could ever fold this plane so they line up with each other, right? What could I do, though?
Rotate.
I could rotate. I could spin either one of those. If I put a tack in the board right there and I spun the board 180 degrees, it would look the same. Agreed? Okay, so it has rotational symmetry, right? The x cubed and x to the 5th. Now notice, and so does, by the way,
What about the
negative powers start to look a little strange. And I'm going to hold off on that for now. We'll get to those later when we talk about inverse functions. But notice that even though y equals x to the 1, it doesn't have the curvature. It still travels through the same points, and it has the same rotational symmetry, right? So here's one just important thing that I just want you to see now, and we'll come back to this later in much more detail. Notice that it's really, you can characterize the types of symmetry and the basic look of the graph by whether these power functions, that's all they are, powers of x, we call these power functions, whether these power functions use an even or an odd exponent. So right here we're looking at, in math we call this a family of curves, of different, family of odd power functions. So this is 3 different examples of power functions with odd powers. They had that rotational symmetry. If we look at the collection of 3 different examples of even powers, they have similar features also. They have the folding symmetry, so we call that even symmetry in math. Okay? All right, so big deal. Well, here's why I'm showing you this. I want you to make a connection, and this is kind of an important connection. Let's look at the function. Here's the function. Y equals 0.000001 x to the fourth plus 0.001 x cubed plus 0.1 x squared plus x. So I want you to tell me there's 4 terms in this function, right? Eventually we'll call this a polynomial, but that's a little bit later on. There's 4 terms in this polynomial function. There's the fourth power, third power, second power, and first power. When I'm zoomed way in like this, which one clearly dominates? The x to the 1, right? So this thing looks, it's most strongly modeled by x to the 1. Agreed? Okay? And here's the original function. I can prove it to you. There's the original function. If I also graph simultaneously y equals x, they line up perfectly, right? So it's settled. If we want to look at the behavior of this function, it's modeled by y equals x. Seems pretty straightforward, right? Okay, well, let's zoom out a little bit and see what happens. If I zoom out, oh, hold on, hold the boat here. Something happened. That doesn't look very linear anymore. What does that look like? Not linear in what way? It looks an awful lot like a parabola, doesn't it? Now, they're not exactly lined up. They're not exactly lined up, but we can see that they look very similar, right? So, okay, well, I guess we were wrong. I guess the dominant behavior is going to be the x squared behavior, right? Let's zoom out a little bit more and just see what we see when we zoom out a little bit more. Oh, man, look at that. What do you know? Trick questions, yeah. So what's that look like?
Looks like that one right there.
It looks a little bit more like the x cubed, right?
But
Okay, but predictably, if I keep zooming out, what's going to happen? Okay, you see what I'm saying? Yeah. So when you get out to a very large scale, the function that it's going to mimic is x to the fourth. Now you might be saying, okay, I get it, but those don't look that similar, right? Well, they will. If I'm gonna kind of tweak the axes a little bit here so we can go out. If I go out real far right now, it's just going to look like it's going to get real skinny, and I'm not going to be able to see much going on. So I'm going to go ahead and warp this a little bit. So I'm going to stretch out the horizontal axis, and I'm going to compress the vertical axis so we can see the large scale behavior a little better on our screen. Does everybody get what I'm doing?
yeah.
So if I go into here, whoops, not there. That's the last thing I wanted to do. I wanted to do instead, I want to go to here, and let's let the x-axis go from something like, how about negative 50 to positive 50. Okay, and now if I zoom out some more from there, let's go out some more. So let's go negative 1,000 to positive 1,000. And let's go ahead and make the y-axis a lot bigger. Let's have it go from, instead of going from negative, what is that, 15,000? Let's go from negative, well, we don't need to go much further down. Let's go negative 25,000 up to positive, I don't know, like 500,000?
Yeah.
Oh.
Okay, now what are we starting to see?
It's just got a little dent.
It's got a little dent, but if we go further and further away, if we keep zooming out, What do you notice? Those, so, I mean, that's actually, how much time we got? 1 minute? 1 minute? Okay, so let me wrap this up. Very quiet, listen up here real quick. So what we see there is, you can see this trend. If I were to keep doing this, pretty soon they would be indistinguishable, right? So the dominant behavior at the tails of the function, as x goes really far to the left or the right, is only that first term, right? Okay, we'll wrap it up tomorrow. You guys can work tomorrow on this.
May I have a follow-up?